Hello again. Tonight we're going to talk about dark photons. You've probably heard of, dark energy and dark matter and all those things. It's just dark is just a way of saying we can't directly observe it. We don't quite know what it is, what's causing it, but we can kind of see an effect. So things we can't observe, we just call them dark. So I've lumped all that and said, well, are there photons that we cannot capture? So I've described these as dark photons. So we know about the things we can't see with the human eye, like infrared and ultraviolet and X-rays and gamma rays. At one point in time, those would have all been considered dark because we had no instruments to pick them up. But now we've developed the technology and sensors for detecting and observing them. But when I first saw a YouTube video on this, I thought, it's just clickbait. Dark photons. Sounds mysterious. Sounds like it could be a sci-fi movie title. So I went looking for other information. And I found that in November of 2023, CERN, the collider folks over in the European Union, decided they were going to be doing some research into, and they actually called it dark photons. So I said, well, if CERN's getting involved, I've got to look more into this. And when I did, first thing I noticed was, there's a bifurcation here. CERN is postulating, this is CERN postulating that dark photons are a new unknown. They're calling it long-lived, but their definition of long-lived is it lasts for picoseconds, not attoseconds. And a picosecond is 1/1000th of a nanosecond, and a nanosecond is 1/10000000th of a second. So you're talking 1/1000th of 1/10000000th of a second, and they're calling that long-lived. And very high energy. If you remember, they were talking about the Higgs boson being in the high energy realm. They're talking about this being in the same kind of realm of 10 to 60 billion electron volts. Now that mixing the word billion with volts sounds like, ooh, that's a lot of energy. Actually, it's not. You lifting a piece of paper is millions of electron volts worth of energy. But so CERN believes we're looking for a new particle out there, one that's not currently in the standard model. And it comes about, decays, and then is not there anymore when a Higgs boson decays to form muons or muons. So that's what they're doing. That's their postulation with dark photons. Mine, on the other hand, is dark photons are residual energy photons. These are photons, no new particle needed. They're just photons, but their energy level is so low, they're like residual energy. They're running on empty, that they can't excite atoms anymore. So there are no atoms in the periodic table of elements that they can excite because their energy level is too low. They are photons. They're not new exotic particles. Once a photon gets into this state and it won't interact anymore, the photon could live for billions of years as indivisible subatomic particles that we can't detect. The particular energy we're talking about here is something that is less than 3.893 electron volts. Now, I didn't just pull that number out of my dark side. I found that there's actually physics behind it. And the wavelength, if you've heard of the gravity waves that we're now able to spot with pulsar timing arrays, the gravity waves are larger than the diameter of the planet. That's how long the wavelength is. These are, mega or million meter wavelengths. So the wavelengths of these very low energy photons would be larger than the diameter of the Earth, meaning their radio frequency would be very, very low, less than 1 petahertz. Now, a petahertz is, if you think of disk storage, you talk about, megabytes and gigabytes and terabytes, and then comes petabytes. So it's larger and larger numbers of counts of things. And when you're talking about frequency, you're talking about numbers of cycles per second. And when you have a very long wavelength, you have a very, very short frequency, a very long frequency, a very high frequency. So we're talking about petahertz. So, these are very long wavelengths, longer than the diameter of the Earth. So you remember me talking about extremely low frequency and how we use that for submarine communications? Because it would go around and penetrate just about anything. So if you can imagine something that's maybe 100 times lower frequency than that, that's what we're talking about, that are dark photons. So photons are subatomic elementary particles that convey electromagnetic radiation or energy. To us, they're light. That's what our eyes take in, is light. But what actually happens is the photons go in and they hit the chemistry in our retina, and they translate that into energy that then becomes conducted across our nerves into our brain, where we have something smart up there that makes images. So photons, energy, wavelength associated with the color of light. So you have both visible and invisible photons. You have those that are visible, like visible light, and then you have the entire spectrum of what's left, which is radio, microwave, which is kind of also radio. You have infrared, ultraviolet, X-ray, and gamma. So dark photons would be well below all of this, well below radio. So it wouldn't be visible to us. It wouldn't be visible to pretty much all the technology we have. So photons are characterized by their wavelength, which is associated with their energy, which we think of it as the color of the photon. How many of those photons you collect together and detect is really the amplitude or the flux. How many? It's not a flux capacitor. It's how many photons per square area are striking a surface. So we're not going to focus so much on the amplitude or the flux. We're going to focus on the energy, the wavelength of photons. So as I was saying, these photons would be invisible, not detected by our physiologic vision. They have wavelengths that are longer than the visible, and then there are also, the high energy ones that are shorter. This is on the lower end range of things. But if we can't see them with our eyes, we can often create technology, imaging sensors and such, that allow us to capture the data, which we can then digitally measure and make pictures from it if we want to. So photons that we can't currently see, we don't think of as can't currently exist. So we identify things as like dark energy and dark matter because we don't really know what they are and we can't directly detect them. So we call them dark. Well, in this case, these are photons whose energy level is so low, we don't currently have any technology to be able to detect them. So I'm calling them dark photons. So if you remember the presentation about very low frequency radio, extremely low frequency, there were things that interfere with it, like power grid, the 60 hertz or 50 hertz, that's everywhere. The microwave background, that's slightly higher energy, but it's also ubiquitous, it's everywhere. But if you get down in the very, very, very low frequencies, there's just no interest in observing that because we have no means of transmitting at that lower frequency. About the best we did was the ELF to submarines, and that was about 60 to 80 hertz. We're now talking about stuff that's down into the small fractions of 1 hertz. So because we have no transmitter, we're not going to pay any attention to creating a receiver. So it's going to remain invisible or dark. So why would it not interact? Well, we'll talk about two things here: excitation versus ionization. If a photon comes in and interacts with the electrons associated with an atom, you can get excitation. That means the electron moves to a higher energy state, a higher energy Bohr shell within that atom. The electron doesn't leave the atom. It just moves up, finds a hole, sits there and goes, I've got too much energy. And then it releases a photon and then drops back down. This is excitation. Now, if you give the atom and the electrons a lot more energy, this is its energy of ionization, it'll actually make the electron spit out of the atom. And this is how you get electricity, is you get electrons moving between atoms and producing an electrical current. Now, there's something called the selection rule, the physics process, that says higher orbitals will have less excitation energy and lower orbitals will have greater excitation energy. So if I want to excite an electron that's towards the outer levels of an atom, it's easier to do that with less energy. If I want to get down into the meatier parts of that atom, it takes more energy to get the electron to go out, and it takes even more energy to get the electron to actually leave, to be ionized from the atom. So these are basic principles of subatomic particles and the fields within an atom that hold the atom together. So for every element, there are these ionization energies and excitation energies, and depending upon what layer you are within the atom, the amount of ionization and excitation differs. So you have sets of numbers, a big database that has all these numbers in it, and there's an organization that actually keeps all of that stuff. Now, when you drop the photon in and it excites an electron, the only way it can do that is if it's the correct amount of energy. So if I take one that doesn't have enough energy, I'm not going to excite the electron. If I take one that's got too much energy, I might ionize the electron loose, but if it's got even more energy, it won't interact with the atom, with the electrons, because they have what is known as quantized energy levels. So the electron in a certain shell is looking for a certain amount of energy to make it pop up, 1, 2, or 3 levels, or it's looking for a certain amount of energy to make it leave the valence electron position on the outside of the atom, the easy ones to get out. So you need to not only have sufficient energy, you need to have the right level of energy if you're going to actually excite or ionize electrons. So what is the minimum, not ionization, but just excitation energy? And it turns out there's a minimum for this. If you look at electron volts, you can convert that directly, because sometimes in science they'll mention things in electron volts, but non-particle physicists will mention things in the SI unit of joules, not named after Jules Verne. But you can see this is a very, very, very small amount of energy. 1.6 times 10 to the minus 19 joules is 1 electron volt. So very little energy. So for the element hydrogen, the minimum excitation, just moving the electron up and down and spitting out photons, the minimum excitation energy is 10.2 electron volts. Still a very small number, even though it's 10. The minimum ionization energy, in other words, to get the electron to actually leave the atom, is higher. It's 13.61 electron volts. But that's for hydrogen. I won't say hydrogen's a special case, but it just has 1 electron and it likes to hold on to it. So the electron volt levels are not the smallest. But there is an element in the periodic table called cesium, or cesium spelled the European style, that has the lowest excitation energy. This is an atom that takes very little to get it to kick out electrons, or to get it to excite electrons. That's 3.893 electron volts, and they had difficulty measuring how low can it go. So there's an approximation symbol there, because there's a whole bunch of digits with like parentheses at the end that says, we got it to about this level, and then it kind of like everybody's observations differed. So I just rounded it to 3.893 about electron volts. So if I said, if I had a photon that was less than 3.893 electron volts of energy, meaning it was one of these very, very low frequency, very, very long wavelength photons, how would it interact with elements on the periodic table of elements? Well, if it's below 3.893, it wouldn't. It wouldn't excite them. It wouldn't ionize them. It doesn't have the energy to do that. So the energy level would be too low to interact. It wouldn't ionize, because that would take a whole lot more energy, and it wouldn't just excite because it's below the minimum excitation level. But that photon would still have a non-zero electron volts value, so therefore it should still have a wavelength and a frequency. Very long wavelength, low frequency.
Monroe,
Yes.
I don't know if this is a good time to ask, but these protons and measurements and wavelengths are being based on here on Earth. Would they still be the same based on another planet?
Yes.
Okay.
The basics
Yes.
of physics and elements of the periodic table. So as far
The
as we know,
and everything
we
will
haven't-
still be at the same length.
as far as we know, from what we see stars, the physics, the subatomic physics we're talking about is the same throughout the galaxy and the universe.
Thank you.
Okay. So if a photon approached an atom and it had less than 3.893 electron volts of energy, that photon would literally just go right through the atom because it doesn't have enough energy to interact with it, and it doesn't have the right amount of enough energy to actually meet that discrete amount of energy it's required to move certain electrons around the atom. So even if we had a bunch of these photons going around some material, the amount of them wouldn't really change the fact that the individual photons have too low an energy to do anything. But the question is, would they still exert a reflection pressure? You know, one of my fond physics topics is radiation reflection pressure. So they still have energy, but they're not going to be interacting electrons of atoms. So would they still transfer momentum to the atom, to the material? I don't know. We need some more scientific research and observations to determine that. So if you're talking low numbers, there is a low number associated with like the hydrogen atom. And when you have the electron like giving up all the energy it wants to as photons, it's now down at the lowest level. That's the ground state of that electron. And for a hydrogen atom, that's multiple times our 3.893. That's 13.6 electron volts. So even if you were talking about a hydrogen atom at the ground state, for a cesium atom, the minimal energy from a photon is a fraction of that. And we're talking photons that have even less than that. But if a photon had less energy than that, would it actually still exist, or would it somehow, dissolve or fade away? Or that we have no evidence that says a photon degenerates if it's left alone. In other words, if a photon interacts with an electron, it can energize that electron, bring it out to a higher level, and then the electron will fall back and spit out a photon. And that's great. But if it doesn't have enough energy to interact, how is it ever going to get rid of the last amount of energy that it has? So low energy photons would essentially be ignored by atoms because they don't interact. They would pass through them with zero interaction, not even weakly. They aren't, if you've ever heard the term WIMPs, weakly interacting particles. Not sure that this is the definition of a WIMP, but they would still have non-zero electron volts. They'd still have a wavelength, but their wavelength would be very, very long. The frequency would be a very low frequency. But they might still produce considerable radiation reflection pressure cumulatively, just not individually. So this was something that Helen suggested me to look into as well. So you have excitation and you have ionization. That's talking about the electrons within an atom, but you can have bonds that are electrons being shared between atoms. These are molecular bonds, and maybe you don't have to have enough energy to split the bonds, but can you make the molecular bond vibrate? Can you make it oscillate? And I did some research into that and said, maybe I need to take a look at this. Maybe we won't energize the electron or separate it from the atom. Maybe we'll not break the molecular bonds, but we might make them wiggle. So I went looking at molecular bond excitation and breaking. Now, to break the bond, obviously it takes a lot of energy, and actually takes not just higher energy, it takes a large amount of flux, lots of photons beating on the molecular bond in order to actually break the bond. So this is what I said, it requires flux And I actually,
And the other one that I just remembered is scattering.
Rayleigh,
Like,
Rayleigh
you
scattering.
absorb some of the energy, you don't change, you don't have much excitation. You just absorb and emit in different directions, just like, the blue sky.
Right, but you still have an electron that's being interacted with a photon of a minimum energy level, and the energy level for scattering is quite a bit higher. So we're talking about the smallest energy levels here. So a lot of these interactions just, you don't have the juice to do it, so to speak. So I looked up the example molecular bond was iodine monocyanide or monocyanide or iodine monocyanide, the ICN molecule, and it requires 307 nanometers, which is in the UV range, very high energy, for 60 femtoseconds. And it requires, I couldn't find the flux number, but it was indicated as requiring a specific flux. Now, that just means you need high energy photons, you need them for this period of time of 60 femtoseconds, and a certain quantity of photons beating up on the molecular bond in order to break the bond. So I don't think we're talking about energy levels here that would be sufficient to vibrate or break molecular bonds. So in the case of not breaking the bonds, but exciting them, vibrating them or causing them to rotate, causing the molecule to rotate, farther apart atoms require less energy to oscillate or break. So when you have a molecular bond, if the atoms are small enough, then the atoms are, if the atoms have few enough electrons, then the distance between the individual atoms is going to be smaller. If you have bigger atoms with more electrons, with looser electrons out on the valence level, then it's much easier to crack them apart and break them and vibrate them. So I looked up what levels would be required to not break, but just oscillate, and 20 joules. And if you remember, an electron-volt was a small fraction of 1 joule. So the vibration energy of photons would be sizable compared to these low energy photons. And when I was looking it up, I found this thing called the Stokes shift. And it turns out that if you have photons that interact at the molecular level and they excite molecules, they excite the bonds, the photons can actually have a small amount of their energy robbed from them, not at a discrete level, by the interaction. So it's much like if I have two atoms that are close together and they're joined as a molecular bond, and then I shoot in a photon and it makes the molecule wiggle, there's an energy transfer. It's got to get it from somewhere. So some of the energy from the photon will be reduced in order to make the molecule vibrate. So this is a Stokes shift is a means whereby the photon isn't fully absorbed, but some of the energy is removed from the photon. So if you keep doing Stokes shift of photons that are not high energy enough to ionize or excite electrons, but they're in that realm below that, sufficient to make molecules wiggle, not break apart, but just wiggle, the Stokes shift will be slowly robbing these lower energy photons of more and more energy until they no longer have the energy level to oscillate or excite molecules. So this is a mechanism whereby you can start out with higher energy and get lower and lower and lower and lower and lower. How low does it go? There's no information as to how low it can go. But once it gets below ionization, excitation, molecular bond breaking, and molecular excitation, that there's nothing left down there to interact with it, but the photon should still exist. So what happens when the photon energy level is too low for the photoelectric effect? So when we want to take observations, we want to capture an image of something, the photons that are coming in have to have sufficient energy to make the photoelectric effect happen in the material that's the pixel. So Photon comes in, interacts with the material, produces an electron. The electron gets captured in the material. And when you have enough photons, enough flux coming in, it will charge up the pixel, the well. And then when you drain it out, you'll count the number of electrons you have. And that's a direct correlation to the number of photons you captured. So that's how you capture an image for a pixel is you're basically doing photon to electron transition because you're ionizing, and then you count the electrons from the ionization. And you might use a low noise amplifier to boost the signal strength if you don't have enough flux, but the end result is photons transition to electrons, store the electrons, drain them out, count them with an analog to digital converter, and that's your pixel amplitude. Not the wavelength, just the amplitude. So if we have a low enough density of low energy photons, it would be undetectable by our pixels. It's not that they're too dim, because that would be flux. Their wavelength is too low to cause the photoelectric effect to produce an electron from that photon. So nothing to see here. So if you have a photon that's greater than 0 electron volts but less than 3.893, you could use the Stokes shift to slice that down below that level until it no longer interacts with molecules, so no more Stokes shift. So you get to this bottom plateau, and the photons still exist. They're not gone completely. They're just so low that they don't interact with anything. So I look for what is another way that we can get this kind of Stokes shift thing, where you can take a higher energy photon and chip away at it until it no longer has enough to interact. And I found it. In physics, there's another thing called the Bethe formula. So when a higher energy photon or proton or alpha particle or ion, which is electrons, when they pass through that giant open space that is an atom, if you ever see the model of how much empty space is inside of an atom, a photon can pass through an atom and not interact with it, even if it's higher energy. But it is interacting with it. So you have a photon that can pass through, and some of its energy would be drawn away, but not enough to cause the electron to move to an outer layer or to ionize the electron. It just robs a little bit, and that photon now has a little less energy. But then I looked at how might this actually be pertinent to what we're looking at here, and the Bethe formula is way more energy than what we will be talking about. So I said, well, if the Bethe formula says, well, we're right on the edge of either exciting or ionizing the atom, we're way below that. So I don't think this would be something that's meaningful. What about relativistic redshifting? So if I have a photon and it's blue, and I take some energy away from it, it's no longer blue, it's now moving down the spectrum, moving down, lengthening the wavelength. It's now becoming less blue, more yellow, less yellow, more orange, more red, infrared, microwave, radio wave. So as you keep chipping away at the photon's energy level, it's going to be moving from higher energy like blue into red. So is red shifting nothing more than the universe chipping away at photons over distance, over time, and making them red? No, the expansion is still a thing. So the expansion moving out is what's causing the red shifting away from us. So it's not, the reduction in energy of the photons down below a threshold level is not relativistic redshifting. But I had to look. So I said, is there some way we can make this artificially happen? If you know about green laser pointers, you know that the cheap ones literally take infrared laser light and run it through a crystal, and the crystal does a doubling and creates a shorter wavelength. So it takes 2 photons in and creates 1 higher energy photon with a shorter wavelength out, and therefore the infrared laser pointer becomes a green laser pointer because it takes the wavelength, it cuts it in half, doubles the frequency, and now you get green out. is there anything in physics that does the other thing? It might, take one photon, split it into two lower energy photons, and yeah, we actually make these things. People make these things. Nature rarely, if ever, makes these things. They're called optical parametric oscillators, and they're used in fiber optic communications because they're a nonlinear optics process. So if I have a particular wavelength of photon and I go, I need that to be a different wavelength. I'm really looking for a different frequency, but I need it to be a different wavelength. What do I need? I need it to be about half of what it currently is. So they can take in a photon and split out two photons, longer wavelength, different frequency. And we've been able to create these OPO devices since 1965. But finding them in nature is really rare. What it's referred to as energy dampening or damping. And the fabric of space in the presence of high gravitational fields can actually do this. It can actually reduce the energy level of photons. The photons aren't supposed to be interacting with the gravitational field, but because of the other effects that we just talked about, it can reduce the photon's energy level by a small amount. But since we're already way down low, the damping is not going to have any effect. It's not going to reduce the photons down to zero. And if you were to reduce the energy level of a photon down to 0 electron volts, would it still exist? I don't know. So what effect would all these photons have that fall below the interaction threshold and are still out there with a non-zero electron volts, but they're not interacting? Well, they could have been around for a long time. They could have been left over from the formation of galaxies, the Big Bang. They could be primordial in their existence, and they're not interacting. So they're not going anywhere. They're just flying around in the universe. Once their energy level falls below our photoelectric effect, we can't detect them anymore. We don't have the technology to do so. So if they were to fall to, let's say, a fraction of an electron volt, we wouldn't have any technology that would allow us to see them. They would be dark by our current contemporary technology. So if they're out there and they can be in large quantity and with low energy, could they be the source of some of the things that we see, like the issue with galaxy rotation from the center of the galaxy to the outer portion of the galaxy? Could it be just the enormous undetected presence of very low energy photons that are still interacting as radiation pressure? Could they be what we think of as dark matter or dark energy? I'm just guessing. Don't know. Don't have any observations to prove it. And as we learned that the Hubble constant is not actually a constant acceleration, it's actually a jerk, which means the acceleration has changed over time. Could that be the source of the Hubble acceleration jerk? Is just the large amount of low energy photons that are producing radiation pressure. And given their ubiquitous presence, I mean, they should be created all the time on a continuous basis by a lot of the matter that's already out there. So they could be ubiquitous. If they do have a radiation pressure effect at a very small level, and if they're doing so ubiquitously throughout the universe, could they be why the speed of light is limited to c? Can't go any faster because the molasses of the low energy photons won't let it run at a higher speed. So the more energy you apply to it, the more radiation pressure you're going to encounter, but don't know. And for those people that aren't into the small and large numbers, I had to have a table. There's no formulas, just numbers. So I put in here the energy of minimum excitation of a cesium atom. And then we get down to lower energies. You can see here it goes from electron volts to pico electron volts. That's 10 to the minus 12 pico electron volts. And then we get down to femto electron volts. and femto is minus 15. And that would be Earth diameter at, 7926.13 kilometers. And now we're talking about wavelengths bigger than the diameter of the Earth. And that's 3 hertz. So 3 cycles per second on that radio dial. We get down to even smaller frequencies, and we get down to fractional energy levels, down to really, really small energy levels. And when you get out to what if the photon had a wavelength of 1 light year, it would be 31.7 millihertz. So that's thousandths of a hertz, and it would still have an electron voltage of 131 atto electron volts. And atto is 10 to the minus 18. So it would still exist. But what about if we took it out even further and said, it's not a light year, it's a parsec, about 3.26 light years. You could still get a frequency for that, and you could still get an electron volt value that's non-zero. Infinitesimally tiny. And we don't have the technology to detect that. We don't have the technology to create that. So we don't have much interest in looking down there because the light's just not good. So my postulation is dark photons do exist. They're photon subatomic particles. They're exotically plentiful throughout the universe. They're everywhere. They're not rare, but they're highly dispersed. Are they the missing mass of the universe? Well, if energy is equivalent to mass, and that's what allows photons to be massless and neutrinos to be very, very low mass, then these would be even lower mass, but a lot more of them. Because they're below the threshold of excitation, they will not interact with atoms or molecules, not even weakly. There's no new physics needed to understand them. They do obey the principles of a photon. They're not a different kind of a spin of a photon. They're not a new property of a photon. They are going to be fractional hertz. So you got to look really small in the radio dial. Maybe we have to create new kinds of radios. They're not going to interact with anything. But individually, they have non-zero energy of mass. Given they're abundant, they might produce enough radiation reflection pressure to be a barrier to or move large objects like galaxies or things wanting to move at the speed of light. But because we have no ability to transmit at these low frequencies and receive at these low frequencies, how hard do we look? How hard did we look for infrared before we realized there's something there? Oh, a thermometer, not complex technology. Ultraviolet, well, we had to create detector technology that could detect it because the thermometer wouldn't do it. What about gamma radiation? Well, we could detect gamma radiation by the large energy that it would transfer. But this is such a small amount of energy. First thing you're going to have to do is figure out how the hell are you going to detect them? Remember, we don't detect neutrinos directly. We detect neutrinos indirectly because they'll interact as they essentially create a shock wave with Cherenkov radiation, and we see the blue light that results from that. So maybe if we can find something that would cause an indirect effect with these very, very low energy photons, we might be able to get it to squeeze out something we can detect with our current technology, but not at the moment. So in conclusion, dark photons do seem to have the potential to exist without us upending quantum and physics technology. It's just another energy level of photon. But given that we're unable to detect them by the photoelectric effect, how do we know that they're there? Like I said, we don't detect neutrinos directly, we do it indirectly. So if dark photons were confirmed and we had a way to detect them, this would be a significant discovery in astrophysics because it might explain a lot of dark things. It might explain why things can't go as fast as we want them to go. And if we could make a material that would create these low frequency photons, which we can in nonlinear fiber optic switching, then by creating these photons, we should be able to see it interacts, and when we drop it down to a certain level, it stops interacting. But how do we know that the photon just didn't go away, didn't fall apart? We wouldn't, because it would no longer be interacting. So, but if we can collect enough of this very low quantity energy in a large enough flux, we might find an abundant source of free energy throughout the universe. Or as I like to create the analogy, if I drop a penny on your forehead, no big deal. You might be irritated, but no big deal. If I drop 5 pennies, one every 5 seconds, still, you're irritated more, but no big deal. If I take a dump truck load of pennies and I dump them all on your body at once, you're a goner. So if you have enough of something very, very small, it can have a very substantial effect. And lots of links to things where I explain what are dark photons versus what they're doing with dark photons at CERN, and then about atomic energy models and electron configurations. And then you can actually go look up the excitation energies for the various chemicals and elements. And then the iodine monocyanide, how I found that out. That's actually in the National Institutes of Health website. And then you can go to the NIST website and look at the actual ionization energies for all the various excited electrons of all the elements in the periodic table. Fun browsing, like reading a dictionary. And then basically work in molecular bonds and how these are broken versus just excited, vibrated. And then if you're interested, what's the Stokes shift and things like that, I've got links to find out information about that. As you can tell, lots of links. I did lots of research. Comments? Questions?
Monroe, can I make one correction on
Sure.
one of the slides? It's the one that you mentioned that photons are, they might be photons subparticles. It's not. It's photon is a photon. There is no subparticle of photon.
No. That's not what I was referring to. I was referring to the fact that a photon is a subatomic particle. It's not comprised of any further particles.
No, you put in one of those. It might be a photon subparticles. You say that the dark. Oh yes, that's the one. Dark photons do exist. They are photons, subatomic particles. They're not. They're like you can keep the phrase being like dark photons might do exist.
So a photon is not a subatomic?
As no,
No, I know that a photon, I know that a photon
it's from the it's a scalar force. So it's like photon is the carrier for the electromagnetic force. So
Okay.
photons are photons. There is no subparticle.
So a
It's a
photon,
scalar force.
a photon has a wave-particle duality, so it's not a particle. And
Yeah.
it is not further divisible, so it's a subatomic particle, much like if you get below an atom, you have further decomposition you can do to protons, neutrons, electrons, but then you can take those further down and you can get quarks.
Yeah, but they're not subatomic. They are something else. They are not atomic. They interact with atoms, but they are not subatomic. So photons
Isn't
might
the
do
definition
exist.
of subatomic just meaning below the level of atomic and of an atom?
Yeah, but
No, they're not a component
they
of
don't
an
matter.
atom. They're not a component, they're not a constituent component of an atom, so they can't really be identified as subatomic. I get what she's talking about.
Yeah, they are not matter.
Well,
They interact with matter, but they are not matter. But it's and I do believe that they do exist because as you lower the wavelength, you're gonna pass to a point that our technology cannot detect. So yeah, I think that's a really cool name that they chose because
you
it's a
mean me.
photon that we cannot detect, but it's there.
And that's different. CERN has a different concept. They're talking about CERN's definition of dark photons requires a new particle. You got to change the standard model. I'm not changing the standard model. I'm just saying when a photon's energy level drops below the threshold of the
Of
electromagnetic
interacting with matter,
can't
they
see it.
still do
It still
exist. It's
exists.
just
It's
we
still
cannot
a
detect
photon.
them.
It's still a
Yeah.
photon. I get what you're saying there, and I need to make a note to clear that up in the when I edit it.
Yeah. And then the other thing, I have an idea by the sound, because I remember the Veritasium posting. Standing waves, you can raise the wavelength. You might be able to detect them if they are pointing in the opposite directions, and they could
Hmm.
even have different wavelengths. But then if they are like detected in a point, you can make a standing wave, and then like let's say you have a very low or like a long wavelength and low frequency,
Yes.
and then if they interact together coming into the other direction, they'd have a addition position, and they become higher and lower, and you might be above the threshold of detection. That's an idea to detect, but I don't know if it's workable if you're detecting everywhere from nature. But that would be
I
maybe
think
an idea, like
that's something to consider. I think you would need quite a lot of them interacting in a harmonic manner in
yeah,
order
like
to,
you can try to produce with something
you know,
and lower the frequency, and then try to capture them raising the frequency. And you can use like reflective surfaces depending what kind of wave. So it's a radio reflective surface that could reflect them, and then try to make them to be a standing wave, and to see if you can um, detect them, because now they are stronger because you're pointing together, in the same
but
direction.
I know it should be possible to take a low energy photon and make it even lower energy using an audio amplifier.
And then like return to the higher frequency.
Yeah.
Like you make it you break the wavelength to make it longer
Mhm.
wavelength and reduce the frequency,
Mhm.
and then find the technology that can reverse the process.
Yeah.
That would be a way to prove their existence.
And Sally was wondering what the effect of magnetism has on dark photons. And I think that gravity can bend the path of a photon. That's how you get, gravitational lensing and such. But a magnetic field itself, I don't think it interacts with light, with photons. Yeah.
No.
Yeah. So I don't think it would have an interaction with magnetism. I don't know that I have the wherewithal to build an audio oscillator to get us down, to take something that might be 3 hertz. If you remember the extremely low frequency submarine communication, you need a lot of square acreage to create the transmitter for a 3 hertz signal. So if the US Navy gave up on ELF communications, and the only ones doing it nowadays are the Chinese and the Russians, I'm not going to do it yourself a 3 hertz transmitter. And if you want to, because I've studied this recently with hydrogen masers, if you want to get resonant frequency amplitude, you can do that with a maser, a microwave amplification by stimulated emission of radiation. It's kind of like a laser, but in radio. So if you were to create an ELF maser, you might get very low energy photons to resonate inside of a cavity, a radio reflective cavity, that could increase the energy output if you reflected them cumulatively enough.
Yeah, but a resonating cavity for very large wavelength. That would be what? The size of
Okay, you would not want to get below 1 hertz. You wouldn't want to get fractional hertz because that would be larger than the diameter of the Earth.
yeah.
You would have to be somewhere uh, probably less than 60 hertz, but greater than 20 hertz. Because that shortens it down where it's only a couple of miles long.
Yeah. So let me ask you something. How did you heard that one first? I missed that one in news.
What, dark photons?
Yeah, that's fun.
I saw it on YouTube as basically somebody postulating, but stating it as if it's physics fact, more so than I tend to do. And I said, it's just clickbait. And the text you could tell was computer generated, and the voice was AI synthesized. So I like, I don't know if this is a thing or not. And then I started searching when I saw CERN actually making use of the phrase dark photons. I was hooked. And then I had to look further into it. And we had a discussion, and you said, okay, it's below what atoms would even excite. How about molecular bonds? And I went, ooh, there's a rabbit hole. So I sunk a few good hours into molecular bonding and what's the minimum molecular bond threshold, and said, molecular bonds are way up there. They're even higher than the atom excitation. Not only that, but they need a strong flux. They need lots of photons beating up on the molecular bonds to get them to break them. But it was a thought. It was a good thought. So I went looking for every possible physics phenomena that could do this. And
So, for what I understand, one definition would be the frequency is so large, and the wavelength so large and the frequency is so low that material would not interact and we would not have any way to detect them. It
yes,
would
you
be
would,
one
you
of
would
the
have a
definitions.
photoelectric effect semiconductor.
Yeah. So in the other definition from CERN, I didn't get it. I didn't understand.
I as soon as I saw they were looking for a new subatomic particle that would redefine the standard model, and it had to do with degeneration of Higgs bosons into mesons, and like, okay, that's a different definition for dark photons. I'll just, you guys go over
Okay,
it.
so it's
Fine.
kind of above our both of our pay grades.
No, it isn't above my pay grade. It's just that's a different topic. That's like a different branch of particle physics. I'm talking about no new particle is needed. It's still photons, just very, very, very low energy, and they're below the threshold of interaction. So,
Okay. Yeah, that's totally understandable, and I think it's possible. You see all the wavelengths coming from any kind. So whenever you see anything like a star, a black body radiation means that that object, a hot object, is emitting all the wavelengths at one time. That's why
a white
most of the
quark,
stars look whitish,
yeah, a white
because
quark.
they're black body radiation emitters, and so they're emitting from uh from the oh my goodness, from the radio to gamma ray. So they are emitting all of it at the
Yeah.
same time. So most likely there is a point where the star is still emitting all the radiation, but it is to the threshold that we cannot detect.
Right.
Even under, or even more energetic, because our atmosphere blocks UVC and blocks gamma ray, so it doesn't come directly to us because we have a protection from the atmosphere and for the magnetosphere. But you have stuff that even in space, they have a threshold from our technology point of view, that if it's like super duper strong gamma ray with the, almost close to, the largest number you can get from gamma ray, where the frequency is so big and wavelength is so short that our technology cannot detect. And
Yep.
then there is the opposite side that would be the dark photons, and I
Well,
think this is totally possible.
in this particular case, the dark photons would behave kind of like neutrinos, and that the atmosphere would not block them, because in order for the atmosphere to block them, the photons would have to interact with the elements in the atmosphere, and it doesn't. So they would likely pass through the atmosphere, pass through the Earth, just like neutrinos do. So yeah, I think they are there. I think that if you think about it historically in physics, we did not know infrared was there until we saw it, and then we saw it everywhere. Same thing with ultraviolet. We didn't know ultraviolet was there until we had a means of detecting it, and then we could see it everywhere. How about the microwave cosmic background radiation? We didn't quite understand the fuzziness on our TV sets, but then, oh, it's not pigeon poop. It's actually microwaves from the early universe, and they're everywhere, and we can map that. Well, this is the same sort of thing. Recently, we've discovered that gravitational wave background exists because we can now detect it. We couldn't detect it with LIGO and Virgo, but we could detect it with the pulsar timing array because it was bigger. Well, maybe we're going to need a really, really big radio receiver, a really big maser in order to see dark photons. But I don't think you'll need an energy source to fire up that maser. All you need is the cavity, because the cavity being made out of even reflective material, how's it going to reflect these things if it doesn't interact with them?
Some Bach nebulas would be useful.
No,
Like dark nebulas would be the cavity for it.
I don't know. But it's certainly something I think that physics should be looking into, because there's nothing that says they can't exist. And there's nothing that says that you can only trim a photon down so far before it just doesn't exist anymore.
Yeah, that is a cool paper to write. It's like
Well, I'm going to put it on YouTube for all to see.
That's a new path for a career that would last your whole tenure.
I can see a physicist going before the National Science Foundation saying, I want to do a research project involving extremely low frequency, and extremely low is a fraction of a hertz. And they go, okay, how much are you going to need? Well, first I'm going to need a radio receiver bigger than the diameter of the Earth. And then they're going to go, get to the end of the line.
Yeah.
So much like the pulsar timing array, probably going to have to find something in nature that can act like its own receiver, its own detector.
Well, we got quite a few free stuff from space.
Yes.
We have gravitational lensing.
Yep.
We have the pulsar timing array. So yeah, maybe we can find a resonance cavity somewhere in space that might work to detect those.
It might be those voids, the voids where there are no stars, where things have been pulled apart. Maybe they weren't pulled apart, maybe they were pushed apart. Individual photons of extremely low energy.
I forgot to post that on Facebook. I read another article that another object that's strange. Some graduation, not even a doctor degree yet. She found on old plate data a circle of galaxies in an area of Booties, if I'm not mistaken, where you see like it's the seventh largest structure in the universe.
Yes.
And it was found in plates, not even on new telescopes, the old stuff. So that's why like Monroe is always saying that if you're beginning career, you cannot get your time on the modern nowadays telescopes, space telescope, and mountaintop telescopes. That is a huge archive of data, including the photographic plates that people can do research. Someone who haven't even finished school already posted and discovered something, and her name is going to be forever in books that people will study forever because she discovered something in photographic plates.
So whenever one of our amateur astronomer friends would take a deep sky image, I was not so much fascinated by the constellation they were taking a picture of, or the nebula or the galaxy. That I would look and just like, you would think that stars would be kind of, if the universe is really flat, uniform, then the stars should be kind of like scattered everywhere. They should be scattered. And then I would go find a group of like 10 stars that were like in a curve, like in a C shape. Like, what caused that? Well, something obviously pushed on them and created an envelope, and those stars formed on the envelope, and then that nebula dissipated, and now you're left with stars that are kind of hanging out together in a curve. So those voids.
Hypernova explosion scars in the fabric of space-time are visible in some pictures. You can actually see those circular areas.
Yes.
And that was like a form of hypernovas. So hypernovas are the very young stars in the beginning of the universe that are exploding before even the galaxy is starting to form. And those hypernova leave like scars in space-time that are like a drop in the water kind of shape. That was really cool, Monroe. I like that one.
Anything else about tonight's presentation before I stop recording?
Well, that's a lot to digest now.
Well, it's going to be on YouTube, so you can spend days going, 5 minutes at a time through it,
Yes.
which is how I create them. Okay, stopping recording.